Okay, so we started this conversation about the whole theory of polynomial functions on probably Monday, and so just a quick review. So recap from Monday. So we identify the polynomial function. And and this is all in your notes. I'm going to write it down really fast. I don't know if you want to copy that. So this is the general form of a polynomial function. So we agreed that um, first term that carries the highest power, that would be your leading term. The constant itself is the leading coefficient. Again, I'm going to write it really fast because this is your notes, so don't bother writing it down. By the way, don't bother writing anything down. Just print the notes after the class. Seriously. Yeah, I'm posting the notes every time. And the notes. Oh, Shaq, that can give you your test back, and then we'll talk about that. Leading. No offense to you personally. And then a sub 0 is the constant term. Well, it's just the reason why I'm saying that when I was a student myself, I was never able to find a balance between listening and writing stuff down. Because if you just write everything down, then you're not registering, you're not listening. But if you just sit there and listen and you don't write anything down, and then there's no record of you listening, and 2 hours after that you just. So at least if you just listen and then you can print the notes and kind of look at them, I don't know. I don't know. Ask your counselors was the best way of doing that. I was never able to take notes and listen to this. At some point I was taking notes right inside the textbook, like on the margins, and that didn't work either. Yeah, I don't know. Yeah, so I don't know. Yeah, so listen. Just kind of write something that, oh, that's kind of nice, so write it down. But just blindly writing everything, then you're not listening. Um, I don't know, don't listen to me. Now listen to me, but not, okay. Anyway, so this is the thing, it's an nth degree polynomial. So that was the verbiage. Then we talked about that end behavior, remember that? How we can determine what the graph of the function looks like in the long run, and it had to do with the even degrees, odd degrees, positive, negative, leading coefficient. Remember we did that little table? And even, and was odd, the positive leading coefficient, the negative leading coefficient, and we agreed that all even degree polynomials look like parabolas in the long run, again with some junk happening in the middle, and all odd degree polynomials look like cubics. We talked about that, right? Okay, so that was all nice and fun, and we played with that. We did a few examples, and then I wrote these 4 statements on the board, and I'll be bringing them up. The equivalent statements that your book doesn't really put them in that list. They kind of throw those extra theorems at you as you go, but it's all intertwined. So the first statement was x equals a is a 0 of a function. Now again, we're dealing with the polynomials here, so it's a polynomial function. Then we said x equals a is an x-intercept of the graph y equals p of x. Then we said x equals a is a solution to equation p of x equals 0. And then 4, what was 4? X minus a is a factor. right? So we have all that. And then we started talking about division there at the end, and you were making fun of me, right? Algorithm, right? That's very good. Division algorithm says that any number can be written as a product of a divisor and quotient plus the remainder, right? That's what we played with. And we're going to apply that to polynomials. But I want to do one more example of how we divide numbers. And this is where you're going to think, well, anyways. So I want to do an example of 1001 divided by, I don't know, 13. And I want to start a conversation on how we use our numerical system, that number 1001. We all understand what that number represents, right? We have no problems understanding that number, 1001. Do you agree with that? Now, we are operating in base 10 when we deal with our numbers. And what this number really means in base 10 is that you have one unit, you have 0 tens, you have 0 hundreds, and you have one of those thousands. Those digits tell you how many of each power of 10 that you have. Because this number can be rewritten as you have 1 of 1000, so 1000 it's 10 cubed, plus 0 times 10 squared, plus 0 times 10 to the power 1, and plus 0 times 10 to the power, I'm sorry, not 0, plus 1 times 10 to the power 0. This is base 10. This is how base 10 works. You have 10 as the basis, and then all powers of 10, and then how many of each power you have. Did you know about that? This is how your numbers work. So like number, for example, 364, that's 300. Okay, I wrote 1,000, but it's 300 plus 6 tenths plus 4 units, right? That's the base 10. The reason why I'm talking about that right now is in order for us to represent a number 1001, we really need those two zeros in the middle, right? We cannot ignore them. Because if we ignore them, 1001 turns into 11, and that's just a big difference. Do you agree with that? I know, because I'm about to do an example eventually, and we'll understand why. Yes, that will be 1001, but this is how this notation works. I mean, I can write any number, I can convert any number to any base if I understand how this base notation works. We can do base 6, then instead of tens you have sixes. And you go 1, 2, 3, 4, 5, 10, but that 10 is really a 6. Okay, anyways. Yeah, well, this is base 10 notation. Okay, if we decide to, some reason we decided to be in base 10 because of, we happen to have 10 fingers. 10 is a kind of a, not a nice base because it's not dividing, not divisible by now. Base 12 is a lot more comfortable. It's easier, but so if we had,
Like other countries with that or something?
What?
Other countries?
No, everybody base 10 because of the 10 fingers. If we had 12 fingers, we'd probably be in base 12 and we'd be a much happier society because it's easier to divide 12. Okay. Anyways, we just had to invent a special symbol for 10 and 11 without writing 1, 0 for 10. We just have to do something else. And then 1, 0 would be actually 12. Anyways, don't worry about that. That's not, I shouldn't even, the online people, sorry. The reason why I'm saying that, if I ask you to divide 1001 by 13, you would, how did we do that the other day? We would put 1001 over here and 13 over there. And we will write 1001 to represent 1001. We would put 0 for all missing parts of our base 10. Right? You all agree with that? Okay. What? Because I'm about to give you a polynomial that has an x cubed and then an x, but no x squared. So there is a 0 for x squared that we'll have to keep track of. Okay, so basically we're going to look at coefficients of polynomials. So if you have a missing power, that means there is a 0 coefficient. So that means, you still have the proper placement of the exponents. So anyways, how do we divide 13 into 10? Doesn't go in there at all. So how about 100? How many times? 7? Yeah, 7 sounds good. So if I put 7 over there, right? So 7 times 13 is how many? 91? Is that right? Is that right? Well, I just don't trust my head here because I'm just doing. So what do you do when you subtract? 91. Look at that. Guess how many times 3? No, I didn't. I'm not that good. 7. Right. So remainder is 0. So 13 divides 1001. Did not know that. Yeah, I didn't. What? She's giving me a hard time. Now, so we're going to try to divide polynomials. Now, the good news in this class and the way your book is laid out, our divisor will always be linear. And that is an awesome news. I'm not going to be, I was planning to divide like a 7th degree polynomial by a 5th degree polynomial. But your book just took it easy and you're just dividing by linear divisor. So that's nice. So that means you're dividing by something smaller. But let me do polynomial division for you. So the long division, and I'm probably just going to do one example for long division, because there's another way to divide polynomials when dividing by linear. Sure, because it's a lot easier. There's another technique. But anyway, so for example, if I want to take 3x cubed minus 4x squared plus 2x minus 7, and I want to divide it by, how does x minus 3 sound? Is that reasonable? So we're going to lay it out just like we did with numerical examples. So we're going to put that little division sign, and then I'm going to put my dividend in here. So 3x cubed minus 4x squared plus 2x minus 7. And I'm going to put a divisor in here. So just like with numbers. And then, when you're ready, the way we do long division with polynomials, we're going to look at the initial term of our divisor and whatever the initial term of the dividend and whatever the initial term of the divisor is, and then just divide them. So what is 3x cubed divided by x? What do you think? What is 3x cubed divided by x? 3x squared. So I'm going to put 3x squared right over here. So I want to keep my exponents lined up. So when we were doing numerical example, when we get a number, when we write something over here, right, we got that little part of the quotient, what did we do next? What did we do with that number? Multiply by the divisor, and then put whatever the product is over here, right? So let's do that. It's a magic pen, right? Should go away? Yeah. So now let's do that. If I take 3x squared and I multiply that by x minus 3, I should get 3x cubed minus 9x squared. Do you agree with that? Well, multiplied by the entire x minus 3. So multiplying by the whole thing. Well, it's the same process, right? As before, when when we got that 7, we multiplied 7 by the divisor. So that's what I'm doing. Is that okay? And then we subtract, right? When you divide, we subtract here. So now I have to be very careful when you subtract. So 3x cubed minus 3x cubed, they're going to cancel. But then keep track of the signs, because this is the weird part. Negative 4x squared minus negative 9x squared. Positive 5. So it's minus 4 plus 9, right? Because there is a double negative. So just keep track of your signs. Negative 4 minus negative 9. Should be positive 5. You agree with that? If I write it on the side, negative 4x squared minus negative 9x squared, I'll get 5x squared. Do you see that? Keeping track of the signs. Now, when you do numerical division, what do you do next? You drop a number down, right? So let's drop that 2x down and repeat the process. We're just going to repeat the process. We're going to divide 5x squared by x. We're dividing the leading terms. 5x squared divided by x. What does that give you? 5x. So I'm going to place positive 5x over here. Okay? Then we'll multiply by the divisor. So 5x times the divisor gives us 5x squared minus 15x. Is that right? When you multiply back? Yeah? And what happens when you subtract? Yeah, so 5x squared and 5x squared cancel out. 17x. So it's positive 2 minus negative 15. So that's 17x. And then drop the last number down. Negative 7 comes down. And then repeat the process. So 17x divided by x gives you what? 17. So we're going to put plus 17 over there. And then we'll multiply again. So 17x. And then 3 times 17 is 51, right? Minus 51. So subtract. What do we end up with? Negative 7 minus negative 51. 44. 44, yeah. So 44. So 44 is our remainder. Well, I just kept dividing. So I went 5x squared divided by x is 5x. And then 17x divided by x is 17. Just like with numerical, you're getting the new problem at each step. You just do it with the first, yeah. But when you multiply by the whole. Well, I can if I want. But I'll talk about this in a second. But this is identical to how we divide numbers. It's just a little messier because I got variables and so forth. But the process stays the same. Now, yeah, so the division algorithm, the one that we mentioned last time, actually tells me that I can take any polynomial and I can express it as, this is my divisor, right? This is the divisor. And this thing right here is the quotient. And this right there is the remainder. So that means my polynomial, whatever the polynomial was, 3x cubed minus 4x squared plus 2x minus 7 can be written as a product of x minus 3, that's the divisor, and the quotient, 3x squared plus 5x plus 17, plus the remainder, which is 44. So this is what we wrote earlier. So any polynomial can be written as a product of the divisor and the quotient plus the remainder. Just like with numbers. Now, since we're only dividing by linear terms, our remainder will always be a constant. It's just going to be some real number. Never going to have excess in it. Because if it does, then you keep dividing by another x. We're only dividing by linear, so we're going to divide by something not linear in a little bit. Not today, though. But for now, when you're dividing by something linear, remainder comes out to be a constant. Is that okay? So did you like that? No. All right, that's good. You're not supposed to. This is awful. This is, it's not the fun process. There is another way to divide polynomials, and it only works. What?
Is it the way where you like write numbers separately?
Yeah.
That's my favorite way to do it.
Yeah, that's everyone's favorite way to do that. And I'm about to show you that. But it only works when you divide by linear. Okay? And since that's our main thing, dividing by linear terms, there is an alternative way to do the division. So I'm going to take the same problem. I'm going to take the same problem. Oops. So there is another way. It's called synthetic division. Only works when dividing by linear terms. Because when we're going to start dividing by nonlinear terms, synthetic won't work anymore. So only when dividing by linear terms. So divisor has to be linear. Now the way that one works, just want to be consistent the way, drop my pen. So the way your book writes it, first, we're just going to list just the coefficients of our dividend. So our big polynomial, I'm just going to list the coefficients. So what are the coefficients? 3, -4, 2, -7. Okay? Now over here, I'm going to put a little number. And that number comes from the divisor. And if I ask you, what number is subtracted from x? What is subtracted from x in our divisor? 3. So I'm going to put that number here, 3. So the negative sign is part of the formula. So I basically do the opposite sign of whatever's in there. So if my divisor was x plus 3, I would put -3. So you kind of do the opposite sign. This is how your book sets it up. You might have seen it differently. I've done it differently before, but the idea stays the same. How many of you know what I'm... Okay. So the way the process works, so see what I did? I just listed the coefficients, and then I put whatever was subtracted from x, so opposite sign. So x minus 3, put a 3, x plus 2, you put -2. So the rest is actually pretty straightforward. First, we're just going to drop that initial coefficient, so 3 just falls through. So we're going to put that 3 over there. And then we'll multiply these two numbers. Okay, so we multiply these two numbers, what do we get? 9, we're going to place 9 over there. And then instead of subtracting, you're going to be adding. So this is the whole idea of switching the sign at the beginning. So instead of subtracting, I'm going to be adding everything. Adding is a lot easier. So if you add the two numbers, -4 and 9, what do you get? 5. Now repeat the process. Multiply 5 and 3, what do you get? 15. Add the numbers. 17. Now multiply 17 and 3. What do you get? 51. Add 51 and negative 7. You get 44. So 44 is our remainder. Just like before, right? What? A lot better, yeah. No, no, no. To know that divisor is linear, just has to be x. Yeah, so that's linear. So that's how you know that your divisor. Your dividend could be anything, but the divisor has to be in the form x minus some number. Yeah, so you do the opposite sign in that little window. Now, it came from my divisor, so that 3 right there. Oh, that one just drops straight through. Yeah. Yeah, really. And then instead of subtracting when you do the division, you're going to be adding here. Now, this list right here, these 3 numbers are the coefficients of your divisor. So they tell you have 17 as a constant, you have 5x's, and you have 3x squared. So they work just like our base 10. You have 17 digits, 5 single powers, 3 second powers, and so forth. So that's how you read that answer. So that's exactly the same as what we got for a quotient. 3x squared plus 5x plus 17. That just gave us the coefficients of our quotient. Okay? So much quicker. But the key here was to remember to kind of do that opposite sign for your divisor. Switch the sign. So if you had x minus 3, you put a positive 3, but you have x plus 3, you put a negative 3. Now, let's do one more. And we're really just going to be doing that syntactic division because it works really fast. The process is really, really fast.
Do you always add, or do you do the opposite?
No, you add. So, yeah, you know, negative 4 plus 9, you just add them. Let me do another example so it might answer your questions. So let's try this. 3x to the power 4 minus 4x squared plus 11x minus 3 divided x plus 2. Okay? So again, we're going to put negative 2 in our little window. Right? We're going to do the opposite sign of what's in the divisor. And then we're just going to list the coefficients. Okay? So what are the coefficients? So where do you put that 0? Right. So you see, we're missing a cube in there. So the coefficient of the cube is 0, and we absolutely must to keep track of those zeros. That's how your 1001 does not turn into 11. So it's really important to put 0 for every missed power. Because if you don't put 0, all of a sudden you just have a cubic polynomial, not a fourth degree. So these are the coefficients, and you absolutely must to keep track of that 0. The 0 was for the missed cubic. And then the process will stay the same. We will drop that 3 down. And then we'll multiply 3 by negative 2 to get negative 6. We'll add to get negative 6. And then we'll multiply again. Negative 6 times negative 2 is positive 12. And then we'll add to get positive 8. And then we'll multiply negative 2 by 8 to get negative 16, and we'll add to get negative 5. And we'll multiply again. Negative 2 times negative 5 is positive 10, and we'll add to get 7 as our remainder. Did you get that? 7 was the remainder. Now, what is the quotient here? Yeah, so it starts with the cubic. So the quotient here is 3x cubed minus 6x squared plus 8 minus 5. That's the 8x minus 5. So that's the quotient. Does that make sense? Any questions on how we did that? Does that make sense? Yes, sir. Well, I was just saying this is the quotient. So this would be the quotient. 7 is the remainder. Basically, what that means that my original polynomial, 3x to the 4th minus 4x squared plus 11x minus 3, can be written as x plus 2 times the quotient, so it's 3x cubed minus 6x squared plus 8x minus 5 plus 7. Right, so it's a divisor times the quotient plus the remainder. Right? Sure, it could be negative, so it would be like minus 7. Remainder could be 0. Remainder could be any real number, depending on the problem. Let's try this. So I want to take x cubed minus 3x squared minus 6x plus 8 divided by x plus 1. So negative 1 goes in the little window. Yeah, do it on your own. And if you're done with that one, I want you to do the same problem and divide by x minus 1. If you did that one, try that one. So same divisor almost, only I'm just changing the sign in the divisor. Instead of x plus 1 divided by x minus 1. So if you get, in the first one, you should get remainder 10, and the second one, remainder is 0. What, good? Did you get 10 and 0? So what does that tell you? Let's talk about this last example when we got 0. Yeah, remainder is 0, so that means x cubed minus 3x squared minus 6x plus 8 is written by the divisor, which is x minus 1, times the quotient, which in this case is x squared minus 2x minus 8. Right? Do you agree with that? So if I ask you, is x minus 1 a factor of our original polynomial, what would you say? Yes, because I just wrote it. It appeared to be a factor because there's no remainders, plus 0, so it's a perfect product. Now check this out. X squared minus 2x minus 8. I can factor that one as well. So all of a sudden, I got my polynomial to factor. That's my division algorithm, that I can always write my polynomials as the divisor times the quotient plus the remainder. The remainder is 0, so there's nothing there. So I was just able to factor this one. I had to use that little division trick. But that's what we're going to be doing in a little bit. We're going to put it in a little more pretty perspective. Now, I also want to ask you this question. I'm going to take this function, x cubed minus 3x squared minus 6x plus 8, and I'll ask you, what is f of negative 1? Can you compute that? Yeah, so how do we do that? Yeah, so negative 1 cubed minus 3 times negative 1 squared minus 6 times negative 1 plus 8. What is that? Negative 1 minus 3 plus 6 plus 8. Yeah? What is that equal to? 10. So f of negative 1 equals 10. Anyone just got a little excited? What makes it a lot easier? But you complete your sentence, because you're saying something. Well, what does this have anything to do with the remainder? Why are you talking about remainder? Yeah, you notice that when I put negative 1 in the window, the remainder came out to be 10. Did you all notice that? You think that one was easier? How about f of negative 8? Let's see, who's going to win? I'm going to do the division, and you'll plug it in. See who gets to the answer first. Yeah, we're doing that. You told me that was easier. Go ahead and go negative 8 cubed minus 3 times negative 8 squared minus 6 times negative 8 plus 8. And I'll do this here. 1 negative 8 looks like a negative 11, positive 88, positive 82, right? Yeah, I know I'm going to win. But what I'm really glad to see that you notice that pattern, that the remainder happened to be the value of the function at that point. The negative 1 gave us 10 as the remainder, and by plugging negative 1 into the function, we also got 10. So same thing here. If I finish this, what is it? 8 times 8, it's 640, so negative 652, so negative 44. Yeah, that will equal negative 644. Let's try it. If I plug that in, so negative 8 cubed. I'm going to throw that in the memory. And then 3 times 64 equals that. So subtract that from the memory. And then 6 times 8 is 48, isn't it? Add that. And then 8. Add that. So yeah, oh, okay, I made a mistake somewhere. Yeah, there's a 6 there, right? Well, that's just me being silly. Sorry. But anyways, so the big thing here, and this is important. Now, first of all, does that make sense? Let's talk about that. How did that happen? Why is that happening right now? Why is there a connection between the value of a function and the remainder? Because before, when we got remainder 10, what is our quotient? X squared minus 4x minus 2. So that means we wrote our function as x plus 1. Yeah. 48? Okay. So negative 4x minus 2, was it? Plus 10. Is that right? So x squared minus 4x minus 2 is the quotient, 10 is the remainder, x plus 1 is the divisor. So we're able to write our polynomial like that. Okay? So if I ask you what is f of negative 1, what happens to the first parenthesis when you plug negative 1 in there? Well, it's going to turn into 0 times whatever plus 10. Well, this is 0 every time. So then f of negative 1 equals whatever the remainder was. Okay? So this gives us what we call the remainder theorem. That when a polynomial, let's say p of x, is divided by x minus c, so by some linear term, then by division algorithm, we get p of x equals x minus c as our divisor times some quotient polynomial plus the remainder. And p of c, if I actually take whatever that number c is and I plug it into my function, it will cancel x minus c. X minus c turns into 0. Then we'll just get the remainder. So the value of your function is your remainder in that case. Okay? Well, sure, but do you understand why? Because if you plug in c in here, you'll just get 0 and you're just left with r, right? And that helps us to find, so that helps us to factor. Because when the remainder is 0, so that's the good thing. If the remainder is 0, that means x minus c is a factor. So we can actually have a little corollary to that. Your book has a name for that. It calls just the factor theorem. So basically, if the remainder is 0, then x minus c is a factor of p of x. Okay, so let me just do a few examples when we actually use these theorems. Because we're going to try to take polynomials that look something like that. For example, x to the power 4 minus 6x cubed plus 2x squared minus 4x minus 3. And I'm going to ask you, is x equals negative 3 a 0 of the polynomial? So there are two ways of doing that. You can just take negative 3 and you can plug it into your function and then see what the answer is, because you want the answer to be 0, right? Or you can run it really fast through the synthetic division. Okay? So if I do this, if I run the negative 3 through the synthetic division, my coefficients are 1, negative 6, 2, negative 4, and negative 3. So what do I get? 1, negative 3, negative 9, positive 27. Is that okay? So positive 29. Now things are starting to get out of hand a little bit. What is it, negative 57? Is that right? You add, you get negative 61. Yeah, looks like that's not going to work, right? Want to multiply that, positive 183, so 180. So is negative 3? Yeah, 87, even worse. Yeah, even worse, right? So 273, so 270. So the answer is no, right? Okay, so no. Let's try another one. How about x to the 4th minus 6x cubed plus x squared plus 24x minus 20? And I'm going to ask you, is x equals 2 a 0? So again, we're going to run 2 through this thing. I don't know if that's going to work. So the coefficients are 1, negative 6, 1, 24, negative 20. So do that one really fast. So 1, 2, negative 4, negative 8, negative 7. What do we get? Negative 14, 10, 20, 0. So what is the conclusion? Yes, right? Agree with that? Now let me ask you, let me add a part to this question. Is x equals 1 a 0 of polynomial? Oh my God. Is x equals 1 a 0? How would we do that one? I can do the same thing, or let me ask you this question. Because right now, don't write this down, because it's really important that you hear me out, what I'm trying to say here. So don't write anything down right now. So right now, what do we have? We have our polynomial written as x minus 2 times, what is this? X cubed minus 4x squared minus 7 plus 10. Minus 7x, yes. Now my question is x equals 1 a 0 of this polynomial? Right? That's the question. Well, my claim is that if x equals 1 a 0 of this polynomial, then it has to be also a 0 of that polynomial, and vice versa. Otherwise, it won't work, right? Because if x equals 1 is 0, then x minus 1 is a factor on this side. Then x minus 1 can only be a factor on that side if it's factor of this cubic here. So it's easier if you found 1 0 already, so 2 is a 0, you continue your synthetic division on whatever the quotients are. So your problem gets smaller and smaller and smaller every time. So do not go back into the original, but use the quotient to continue your division. Because see what happens. If I run the synthetic division again, but just through my quotient, so if I just put that 1 over here, and I'll just do the synthetic division again, see what happens. 1 comes down, so we get 1, right? Negative 3, so we get negative 3. What do we get? Negative 10. We get negative 10, so we get a 0. Right? So that means x minus 2 is a factor over here. So x minus 2 is a factor. And also, x minus 1 is a factor. So that means my original polynomial has 2 factors already, x minus 2, x minus 1. They're both factors of my polynomial. Now what's left? What's the other term? It's whatever this quotient is, right? What is that quotient? Right. So right now, I got my polynomial to look like that. Okay? Is that okay? What? No, I don't know. He keeps laughing and making sounds that I don't like. All right. So, but do you see what just happened? We ran the division twice. Now, why is that a good news? Because if I ask you this question, well, I didn't factor it completely yet. Well, that I don't think I can. Oh, can I? Yeah, that one is nice as well, right? Oh, that's even better. Thank you. How do you factor that one? Plus 2 minus 5. Yeah, thank you. I didn't even realize that one. So then what are the, what? Good. So what are the solutions to this equation then all of a sudden? Can you tell me the solutions to this big ugly equation? X equals 2, x equals 1, x equals negative 2, and x equals 5. Right?
Didn't someone hint to the other ones too, though?
Thank you. Because I was going to say, well, you know, yeah, but they gave us kind of 2 zeros, because if they didn't, we would be in a whole big pain right now. Right? Because, well, technically you have, but yeah, you have to do that without knowing what those are. This was just a little bit of help. Now, but But keep that one in mind. Do you understand what just happened? I mean, this whole idea. They gave us, okay, is 2 a 0? And we ran the synthetic division. We got 0 for the remainder, so the answer is yes, it's a 0. And then they gave us, well, how about 1? Is that going to work? So we ran 1, but through the quotient. And that is the biggest thing here, because if you run it back through the original, well, you just say yes, and then you're still left with some ugly quotient. But this allowed us to reduce our original problem, which was the 4th degree, to a linear, and a quadratic, right? Well, this quadratic happened to be factorable, but if it didn't, would that be a problem if we had a quadratic? No, we have a quadratic formula to solve those quadratics, right? No, no, no. No, it's just too many options. No, how would you? Well, I don't know. Let's. Well, if my question was what are the zeros, then you would take that quadratic and set it equal to 0, and then use the quadratic formula. Well, let's try that, what you were suggesting. I don't know why. I don't know. It might work. So if we go back all the way back to our original one, so 1 minus 6. Don't write this down. 24, negative 20 was it? Is that right? Was that negative 20? Yeah. So you want to work it backwards, right? So this has to be 20 then, right? That was what you're saying? Yeah, but you see here, you don't know what that was because it was multiplied by that. But that was a very good way to think. Um, okay, let's do a little break. I kind of went a little over. So let's do a little break and then we'll talk because you're. Okay, well, let's not take a break then. I don't know about 10 more minutes, but. Well, yeah, we already went over like by 15. So, yeah, no break. Good. I like that. You redeemed yourself there. Um, okay, let me do one more problem where life is kind of good when they toss us few answers. Oh, sure, we probably do need a break. Do we need a break? Okay. Um, what was that? Let's not. Um, how about this one? X to the power of 4 plus 4x cubed plus 2x squared minus 4x minus 3. And I'm going to test these two numbers. X equals 2. I'm sorry, not 2. I'm going to test x equals negative 3 and x equals 1. Yeah. Again, don't, yeah, okay. You can do it on your own. I'll do it on your own. Then we'll match. Hmm? Oh, I know. Well, I'll get to the point where I don't give you the answers. But are you getting that? Get that? So yes and yes. So that means our polynomial, x to the fourth plus 4x cubed plus 2x squared minus 4x minus 3 right now is x plus 3, x minus 1 times whatever that is, which is x squared plus 2x plus 1. Is that right? Can I factor that one? X squared plus 2x plus 1? Can I factor that one? So x plus 1 squared, right? So then what are the zeros of this function? So negative 3, 1, and negative 1, right? Can I sketch the graph of that thing? It's an even degree polynomial, right? It's even degree polynomial, so it goes up on both ends. The zeros are negative 3, negative 1, so those are my intercepts, and 1, right? What's the multiplicity of negative 1? 2, because of the power 2. We know at negative 1, the graph will bounce off the x-axis, right? Not necessarily from the top, but when you connect the dots, it will do something like that. It will bounce at negative 1, and it will go up. That doesn't look pretty. So we had negative 3, negative 1, and 1. So the graph looks like that. So it goes through negative 3 and positive 1, and it bounces off negative 1 because of that multiplicity. How about that? Is that okay? Because again, you're absolutely right. You're given a few to begin with. But let's say that's too nice. Yeah, how about this one? X cubed minus 4x squared plus 4x minus 16. That's the polynomial. So let's call it, that's our f of x. And then one of the zeros, I will make sure I wrote it right. We can probably factor it. But how about x equals I? We haven't done something like that yet. No, we do the same thing. I just want to make sure I wrote the problem right. Well, you do the same thing. You put I over here, and then you put the coefficients. It's not gonna be fun to do because of the I, but 1 comes down, right? Yeah, that's I is like imaginary. So multiply 1 and I, what do you get? I. So when you add them, you'll get, well, negative 4 plus I, right? Well, then we're going to multiply I by that. Let's do this on the side. That's a little tricky. So I times negative 4 plus I. So this is negative 4I plus I squared, right? If you multiply them. What is I squared? So we get negative 4I minus 1, or minus 1 minus 4I. That doesn't matter. So I'm going to put it here. Negative 1 minus 4I. So when you add, what do you get? 3 minus 4I, right? 3 minus 4I. So multiply again. So I times 3 minus 4i, we'll get 3i minus 4i squared, right? So it's 4 plus 3i. Right? Because I squared is negative 1, makes negative 4 positive 4. What was that? No, there are no x's. Did I write an x? Is that what you're asking? No, we're not messing with x at all. Those are just coefficients. No, not yet. No zero, no x's yet. Later. But anyways, did we get 0? No. So is I a 0 of our polynomial? No. Okay. Well, that was fun. Let's try negative 2i. How about negative 2i? Let's run that one. So what are the coefficients? 1, negative 4, 4, negative 16. Is that right? So 1 comes down. Yeah. 1 comes down, so we get negative 2i over here. Right? Then we add the 2, you get negative 4 minus 2i. Is that okay? So now, when you multiply this, you have negative 2i times negative 4. What's that? 8i. And how about negative 2i times negative 2i? What is that going to give us? What? 4i squared, and I squared is? So then it's negative 4. Is that right? And if you add them now, what do you get? 8i. And negative 2i times 8i is actually positive 16. So then it comes out to be 0. Oh, you can go anytime you want.
What's is the final answer actually the bottom or not?
Well, let's just say the final answer for now is just yes. Okay? So the question was, is negative 2i is 0? Yes. That's all we've accomplished. Yes.
But in the class,
Yeah, the last one was no, is a 0. Because that gets really messy. We really want to avoid dividing by the complex numbers and so forth. Because there'll be a way to, I mean, we can do this one by factoring, right? We can factor that one by grouping, can we? What can I pull out of the first two terms? X squared leaves us with x minus 4. What can I pull out of the next two terms? So 4 leaves us with x minus 4. So we get x minus 4 and then x squared plus 4. Right? We set that one to 0, x equals 4. We set that one to 0, x squared plus 4 equals 0. So x squared equals negative 4. So x is plus or minus the square root of that. So x is plus or minus 2i. Okay? Now, a thing about that, when you get those complex solutions with imaginary parts, they only come with a conjugate friend. So if 2i, if negative 2i is one of the zeros, then positive 2i is also one of the zeros, always. Okay? So complex zeros so conjugate pair theorem, I guess. So if a plus bi is a zero of polynomial p of x, then a minus bi is also a zero of p of x. So your complex solutions, the one that have the imaginary parts, will always come in conjugate pairs. Okay? Always. So if you have a 2i, you're going to have a negative 2i as well. Where do you go? All right. I have. All right. Do you want your test? Okay, well then stay. When did you learn that last year? Oh, never mind. Okay, so I want to do this example. Find a polynomial that has the following zeros. X equals 2, x equals negative 3, and x equals 1. So what do we know? If 2 is a 0, then what is a factor? X minus 2. And if negative 3 is a 0, then what is a factor? X plus 3. And if 1 is a 0, what is a factor? X minus 1. And again, it could have any coefficient in front that wouldn't affect the fact that those are the zeros. So a could be any number. I can just say a equals 1. So one of the answers would be just that. X minus 2, x plus 3, x minus 1. If we were to expand that, I don't feel like doing that, but it will be x squared plus x minus 6 if I FOIL this out. And then I'll have to multiply it again, so x cubed minus x squared plus x squared minus x minus 6x plus 6. I'm just FOILing. So x cubed minus 7x plus 6. So that will be one possible solution, and that's okay. That's a polynomial that will have those 3 zeros. Is that okay? A could be any number. So I just decided let a equal 1, because the question was find a polynomial that satisfies that. So if a equals 1 will be one of them. You can make a equals negative 12 if you want to. It'll just be a little messier. But the idea was if something is a 0, then you get the corresponding factor. Okay? Does that make sense? Yeah? So what if I ask you this question? Find a 4th degree polynomial that has zeros x equals 1 and x equals 2 minus I. So what do I need to do? Okay. Is that it? That's not it. Okay, so you tell, okay, good. So x minus, let me just write it like that for now. But you're right, it's going to switch the signs to make it x minus 2 plus I. So it's x minus whatever the 0 is. Is that it? What else?
X plus 2.
Yeah, so x minus whatever the conjugate is. So again, if 2 minus I is one of the zeros, then 2 plus I has to be one of the zeros as well. Is that it? Now, one of them has to be squared. Why do you say that? Because it's a fourth degree polynomial right now. We only have a third degree polynomial. So if you were going to square one of them, which one does it have to be squared? Why is x minus 1? Well, that's not the reason. That's never the reason. Why? You're right. It has to be x minus 1. Why is that one? Otherwise, we're going to need another conjugate. So then we'll end up with like a fifth degree or whatever. So yes, so the only one that we can toss the little 2 on top is x minus 1 squared. Now let's expand all that. See what that equals to. So I'm going to teach you how to multiply really fast. So let's distribute that negative. It's x minus 2 plus I, x minus 2 minus I, right? Okay, so how would you go about multiplying all that? You can always do the FOIL. That will work. A little long. Now we all know how to multiply the first parenthesis, right? How to get rid of the square? How to square x minus 1? What is that going to equal to? Minus 2x plus 1. Okay, now the other two parentheses, there is a way to multiply those really fast. Those two parentheses are not the same. Do you agree with me? They're not identical. Where do they differ? Just the sign of the I, right? So we have a plus and a minus. Do you agree with that? So if I treat x minus 2 as a whole and I is the other part, I can use the difference of squares formula. Because I have two things that only differ by a sign, and using a difference of squares formula, I'll get x minus 2 squared minus I squared. Is that okay? Difference of squares. So I'm treating x minus 2 as a whole. So it's a squared minus b squared. Now, how do you square x minus 2? X squared, 4x, plus 4. And what about I squared? What is that equal to? And then there's already minus there, so plus 1. So this is where we're at. X squared minus 2x plus 1. X squared minus 4x plus 5. Right? At least we don't have any more i's. Right? I's are all gone. So that's why we needed that conjugate. And then you just FOIL that, and there's just no easy way of doing this. So x times x squared is x to the 4th. X squared times 4x is negative 4x cubed. X squared times 5 is 5x squared. Negative 2x times x squared is negative 2x cubed. Negative 2x times negative 4x is positive 8x squared. So it's kind of a long process. What is that? Negative 10x. And then times 1, so it's x squared minus 4x plus 5, right? Minus 10x? Yes, you're right. I wrote plus 10x. Okay, so combine like terms. What do you get? X to the 4th How many cubics? -6. How many squares? 5, 8, 1. All pluses, right? So 14. And x's, -14x. And just the lonely 5. So that will be a 4th-degree polynomial that has those zeros. So you see what we had to use here? We had to realize if 2 minus I is 0 and the 2 plus I has to be 0, and only gives us 3, so we need to fix the multiplicity, and the only one that we could square was that real 0. We couldn't square the imaginary one, because then we'll add another conjugate. Is that fun? Why not? Oh, it is fun. I'm gonna bump your quiz a little later. You're not ready to take the quiz by Monday. But you're ready to accomplish homeworks, whatever and whatever, 8 and half a 9 at least. And well, the homeworks don't have due dates. Yeah, right. There's no quiz due Monday. I'm not saying that I don't know when it's going to be due, but so not Monday. And I'm going to do the same thing for the online guys. I don't know. How are their online people? I haven't heard anything from them. Are you guys doing okay? Say puppy for extra credit. Type in puppy. Didn't we try that before? 5 extra credit points for typing puppy. All right. Oh, believe me, I'll give you the extra credit option. Don't worry.